Okay, well, thanks again for being there. We will continue with the morning session. So this time we have Rachel that is talking to everybody here from the UK. I just want to have a quick observation. For example, not only the students are distributed, but also many on the structure. Just a few minutes ago, we heard about Gather Town, sorry, by Jutta, that is talking from Germany. Many of us are here in France. So that's very cool also. I wanted to just remind that to everybody who is watching this. So please, Aresha, just whenever you want, thank you very much for this keynote, and please just start yourself.
Amazing. Thank you so much, Arturo. So yeah, I guess I'll start by thanking the organizers so much for having me here today. Yep, I was supposed to be in person with you all last year, but things are quite interesting these days. So thank you again for extending the invitation this year. So my name is Rachel Ainsworth. I am based at the Software Sustainability Institute and the University of Manchester in the UK. And today I'm going to be talking to you about reproducibility and open science. These slides are already available online. I shared the link in the Slack, but they're also linked on every slide in case it's easier for you to view them on your own machine, in case the YouTube video is quite small. But yeah, I'll go ahead and dive right in. So today I'm going to briefly introduce myself before diving into the subject of reproducibility, research culture, and open science, and basically what barriers exist to open science and how we can overcome them to reap the benefits of practicing openly. So I'll walk through some example workflows of how to open up your research, as well as share some examples in astronomy. And then because this topic is so big and there's no way I can cover everything, I'll leave you with some more information, some links and resources, and some final takeaways at the end. So just to quickly introduce myself, again, I'm Rachel. I am a research software community manager at the UK's Software Sustainability Institute. Prior to that, I did my PhD in astrophysics, radio astrophysics to be specific, where I studied how stars like our sun form using next generation radio interferometers. So I still kept a link with the radio astrophysics community. I'm part of the SKA Regional Center Steering Committee for the Science Archive Working Group, helping to promote open science within SKA, which it's already quite heavily valued and embedded. If you want to hear more about my sort of research background, I've linked a video to a talk that I gave at Blue Dot Festival a couple years ago. And just generally, I'm very passionate about openness, transparency, reproducibility, well-being, and inclusion in STEM and research. I talk about it a lot more than I talk about my own research, which is how I kind of ended up on this sort of career shift out of research into more researcher support. So I'll talk a bit more about that on the next slide. But if you want to hear me talk a bit more about research culture, I was also invited to give a TEDx talk on the subject, and I've linked that there as well. But yeah, so now I work for the Software Sustainability Institute, which is the UK's national facility for promoting the advancement of software in research by cultivating better, more sustainable research software to enable world-class research. So in short, our motto is better software, better research. As a community manager, I manage the Institute's fellowship program to engage with and support natural ambassadors of better software practice in their research domains. So I really love this job because not only do I get to talk about open science and better software practices and better research practices, but I can also empower others to do so as well. And so we have a really inspiring group of fellows who are doing this work to cultivate better practices domains, and it's not just physical sciences, it's all research domains that we cover. So it's very inspiring to hear about the work going on in other areas as well. And I also manage our annual unconference, the Collaborations Workshop, which brings together researchers, developers, innovators, managers, pretty much all stakeholders within the researcher community to explore best practices and the future of research software. So it's a very hands-on, interactive unconference. We've been online the past 2 years, but hopefully we'll be in person or hybrid again soon. So maybe I'll see you there in the future. But if you want to learn more about the Software Sustainability Institute, you can just visit us at software.ac.uk. So On to today's subject, reproducibility and research culture. So in different domains and even in different literature, reproducibility can mean different things. And often it's interchangeable with words such as, replication or repeatability. A lot of RE words get thrown around. And so to be really explicit about what we mean for this talk, reproducible research means that results can be independently verified from the same data and the same code or software that the original team used. So for instance, a referee can take your same data set, your same analysis, and get the same result that you presented in your paper. That's what we mean by reproducible in this talk. Replicability could mean that you can use the same analysis, but on a different data set to verify the results. And then, of course, in science and research, we aim for our results to be more robust and generalizable and stand the test of time in different analysis methods and different data sets and observations. So you're probably wondering why I'm giving you a vocabulary lesson this early in the morning, but since each of these definitions should be quite fundamental to basic research, these are all things that we really aim for as part of the scientific method. But not one of these aspects is currently incentivized, supported, or rewarded in the current academic system. So out of 1,500 researchers surveyed in this Nature paper or article, 90% believe that there is a reproducibility crisis. And whether or not crisis is the correct word, a lot of people believe that there is a problem. In physics, 70% of researchers have tried and failed to reproduce another scientist's experiments, and more than half have failed to reproduce their own experiments. There are a lot of factors believed to contribute to irreproducible research, such as selective reporting and the pressure to publish, which were among the top. Issues such as low statistical power, insufficient mentoring, but another one is the unavailability of methods and codes. So a lot of these factors come from a lack of openness or transparency and cultural factors. A quote from the paper is, "Failing to reproduce results is a rite of passage. When I was a student, I tried to replicate what looked simple from the literature and wasn't able to. Then I had a crisis of confidence, and then I learned that my experience wasn't uncommon." And that's a quote by Marcus Manafo from that same paper. And when I read that, it just immediately resonated with me because I had the same issue. During your PhD, when you're trying to build off of the previous literature, you can get really stuck and lose confidence if you're unable to reproduce something, and you internalize that a lot and you think it might be you, but it's quite standard. It is quite difficult to reproduce other people's work, and this is hampered a lot by a lack of openness. So for instance, if a paper doesn't share the data that it's used to get that result, that can be a huge problem. And in physics or astrophysics, that might not be the end of the world, but this can have real world implications in other research domains. And just in general, we all need to, work together to improve the reproducibility of our research. And in order for research to be reproducible, it does need to be open. So traditionally, a research paper is meant to contain enough information to allow for reproduction of the results. But as research becomes more computationally intensive, more data intensive, research articles alone cannot contain the full picture or enough information, such as computing environments, to allow for successful reproduction of the results. So although just because sorry, let me back up for a minute. So here we have a reproducibility spectrum published by Roger D. Peng on his ideas on how computational science can be more reproducible and the steps that we need. And so even though we want to achieve things such as full replication and robust research, reproducibility has the potential to serve as a minimum standard for judging scientific claims when these more robust methods are not possible. You know, as we have more computationally intensive research, it can be quite expensive, you know, and resource intensive to try and reproduce results that were obtained using, you know, high performance computing and other methods such as that. So these are the steps that we can take as a minimum to ensure reproducibility of our research. So, you know, in addition to the publication, it's good to include things such as the code or the software that was used to get the results. Adding your data is even better. But then, of course, you know, just because something worked on your computer doesn't mean it works on somebody else's. So being able to share your full computational environment along with all of the software and data that you use is really important these days for reproducible research. And I'll just stop here for a minute and just say that just because something is open or available does not mean that it's fully accessible, transparent, or reproducible. But there are these steps that we can take to improve at the minimum the reproducibility of our research. So I'll talk about research culture for a little bit. There are a couple of initiatives in the UK right now looking into research culture. One of them is the Royal Society, who defines research culture as encompassing the behaviors, values, expectations, attitudes, and norms of research communities. So it affects who does research, what research is done, how it is done, and how it is disseminated. And during this policy project that they're working on, they've investigated ongoing concerns around issues such as research integrity, career paths, permeability between sectors, recognition and reward, diversity, and support for collaboration and interdisciplinarity. And all of these issues they have found to have the same underlying causes: a highly competitive environment and very narrow definitions for success. An initiative by the Wellcome Trust, also based in the UK, has found similar results. So they surveyed a bunch of researchers in the life sciences, and they also found that this highly competitive environment and poor research culture is leading to unhealthy competition, bullying and harassment, and mental health issues. So there's some statistics there from their report. 78% of researchers think that high levels of competition have created unkind and aggressive conditions. Nearly 2/3 of researchers have witnessed bullying, harassment. Many have experienced it themselves. Many don't feel comfortable speaking up, and many doubt that appropriate action will be taken. And a really important statistic, I think, is that just over half of researchers have sought or have wanted to seek professional help for depression or anxiety. And so I bring this up because there will be people attending this summer school who have had these experiences or will have these experiences if we don't work together to shift research culture to be more kind and inclusive, to, you know, value reproducibility and the process by how research is conducted over, you know, the quantity of research conducted. So I'm really excited that Escape has a lot of these values embedded in their project and are promoting this at the summer school. Because I hope that, you know, reproducibility and changing how we do research in science can really shift how people are treated within research and science, and a gateway to a more supportive research culture. So how do I think open science can help this? Well, open science is the practice of science in such a way that researchers can collaborate and contribute, where research data, lab notes, and other research processes are freely available under terms that enable reuse, redistribution, and reproduction of the research and its underlying data and methods. And again, this sounds like it should really just be science without that, you know, open word in front of it. But because of the more traditional way that research is conducted, and because of this poor research culture that's been investigated by various funders and policymakers, we really do need this movement on open science to change how we do it. So open science is, you know, focused on increased rigor, accountability, and reproduction for research, and it's based on the principles of inclusion, fairness, equity, and sharing, and ultimately seeks to change how research is done, who is involved, and how it is valued. So open science encompasses a lot of various different aspects. So some things can include open access to publications, open source software, open data, things like open educational resources and citizen science. But it's also really important to remember that how we open science is vital. We need to make sure that how we research and how we change how we research is equitable. We need to, make sure that we are inclusive of others and just be mindful of who hasn't been included and what structural changes that we need to make in order to make this process inclusive of everybody. And this has been just completely highlighted and showcased throughout the global COVID-19 pandemic, where it's really proven the worldwide emergency and urgency of fostering an equitable access to scientific information. So the fact that data and software has been shared throughout this global crisis has just shown how important that it is in order for us to get through these global challenges together. So why aren't we doing this already? Why are we not practicing science in a more open and transparent way? Well, there are a lot of barriers standing in our way. The big one is that there's a publication bias towards novel findings. So, it's quite difficult to publish, null results or maybe even negative results or things that didn't support your hypothesis. A lot of journals, are focused on their impact factor. They want things that grab headlines, and so a lot of journals have this publication bias towards new and exciting discoveries and results, and that can have negative consequences in the fact that if null results are not shared, then that can create a duplication of effort. Maybe you've asked a research question, you found the answer, but it wasn't good enough to get published. Well, another researcher might be asking the same question, and then they're wasting that effort trying to solve the answer, and then that also doesn't get published. So it's this real knock-on effect and creates a lot of duplication of effort. There are barriers such as challenging the establishment, following the status quo to succeed. So, there's this traditionality in the way that research has been conducted for years. A few other barriers include a perceived lack of reward. There's no incentive to work in this way because it's not considered for promotion. Another is, lack of awareness and training. It requires additional skills and it takes time. Although we're happy to tell you that your attending the summer school will give you those additional skills that you need to practice this way. Other barriers to open science involve a lot of fear. So I've heard things like people being afraid that if I, make my data open or if I share, my code, then I'll get scooped or my ideas will be stolen. I won't get, the right credit for my ideas. And I'm going to show you that shouldn't be the case or isn't the case. But I think the big fears come from, people finding errors in your research and your methods and your risk to your reputation. It can be quite scary to, share your data and your code, especially if you're a young researcher just starting out. You don't want people to find mistakes, but that's what science is all about. We want to catch the mistakes. We want to work together to build upon results and the methods of what people do. So we need to make it okay to be human in the scientific community. And so that's where a lot of this culture shift needs to come from. We need to make it okay to make mistakes and learn from the mistakes and build off of that. And I won't go into this talk, but a lot of great discoveries have been made based on research mistakes. So why should we overcome these barriers to practice openly? What benefits do we hope to obtain? Well, there's a lot, and I really love this infographic from Nature on the benefits to sharing research data, but this isn't just for research data, this is for all research outputs, in my opinion. So just bear with me, I'm gonna read some of these out loud. So there are lots of benefits for individual researchers, such as, if you share your research outputs, it increases visibility, leading to greater discoverability. It reduces inefficiencies because it's easy to build upon. You can get more citations because of that greater discoverability. It improves output connections, and you get greater recognition. It can increase validity, increase usage, so other people can use your data, which therefore increases the longevity of research and improves credibility because others can have their eyes on it, and we can all verify the results together. Benefits for research communities is that it can increase the resources and new collaboration opportunities. It improves future research, improves the long-term archiving, enables replication. It benefits teaching. If others have access to your materials, they can teach others on how to do things. It reduces unneeded experiments, and we have a greater understanding of research. And then finally, benefits for society is that it can increase trust in research. So if you're sharing everything about your research methods and your data and your software, it can be viewed at by society. And this is also extremely important, again, in the context of the global COVID-19 crisis, is we really are seeing and witnessing kind of a lack of trust in science, and therefore, some people might not be willing to get vaccinated and other things like that. And so it's hugely important, and it has real world consequences. So we really want to increase trust in research. Openness can inform policy, enable public understanding. It'll have economic benefits, easier access to research, your innovation increases, and you can promote citizen science. So there's just so many benefits to sharing your research outputs. And I love this quote by Julia Stewart-Lowndes in her article, Open Software Means Kinder Science, where she says, "It is about mindsets and culture. An unsung part of open software are its communities that promote and enable a more inclusive, kinder culture." So I think that could be a huge benefit of openness is the culture that it then nurtures and fosters. There are also, of course, a lot of selfish reasons to practice openly. So it's been shown that openness and open research is associated with increases in citations, media attention, potential collaborators, job opportunities, and funding opportunities. So these are significant benefits to researchers relative to more traditional closed practices. And then, of course, your primary collaborator is yourself 6 months from now, and your past self doesn't answer emails. So, think about the situation where, you've written up your results in a paper, you submitted them to a journal, and then you begin that lengthy peer review process. It might be a few months before you hear back. But, sometimes you get that review back that's like, oh, can you just do this or, tweak this and change this a bit. And it's just so much easier on yourself if you've worked in such a way that you can easily adapt and edit your methods and your process. And because it's reproducible and you followed, reproducible methods, it's easy to regenerate exactly what's been asked for. So if anything, open science and reproducible research has a lot of selfish benefits for the individual as well. So I've talked a lot about, what is reproducibility, about research culture, and about how I think open science can help. So how can we do this? So we're going to go on a journey on how to share, our data, our code, our tools, and our results in order to make our research more reproducible, which is better for science and better for research culture. So I'm going to be going along our reproducibility spectrum that we introduced at the beginning. So the first thing that you can do is publish your research articles open access. So there are a couple different routes for this. There's gold open access, which means that you publish in an open access journal or you pay the extra fee so that your article and your publication is not locked behind a paywall. That can have high charges and that can limit who can publish in this way. But there's another route you can take called green open access. And the physical science community is really good at this and has been ahead of the curve in this area for a long time. So we have the archive, and it follows the Green Open Access route in that you can self-archive a version of your manuscript in a repository. So archive allows for this. And there are a couple different points along your research journey where you can do this. So you can share a preprint of your manuscript before peer review. And I highly recommend this. This is a really great way to get additional feedback from the community about your methods and your results. It avoids that email after you submit it to the archive, saying, oh, why didn't you cite this? Or did you look at this? You can get that input, before peer review. Or you can share a post print of your manuscript after peer review. So, once you get that review back from the journal or it's been accepted, many journals allow you to then deposit that version into the archive and into a manuscript repository. And there's a lot of community happening around preprints, such as journal clubs and reproducibilities. So it's a really great way to read about and learn about, the cutting edge of what's coming out in the research that's being done. And there's also been evidence to show that sharing your publications open access, and in particular in depositing them to archive, you do get an increase in citations. So this paper here has shown that, by submitting a preprint to the archive, it's already obtained 20% of the total number of citations that, a paper would eventually collect, by the end of the following 2 years. And so this can only benefit you. It gets eyes on your research sooner. It can take months, sometimes years, for a paper to get published in a journal. So sharing your results as soon as possible can only help you, and it can only help science. And I'm going to show this in action a little bit later. So next on our reproducibility spectrum is sharing your code or your software along with your publication. So my next piece of advice is to open source and version control your methods. So version control is the practice of managing and tracking changes in source code and text files, such as through using Git. And you have some talks by Maximilian, I think they're tomorrow. I highly, highly recommend this. Version control is at the foundation of reproducible research, and it's such an amazing tool. And it's just, I cannot rave about it enough. So it's definitely something that you should really focus on and practice during the summer school. But what it does is it stores a history of changes and who made them, allowing you to revert or go back to earlier versions of those files and understand how contributions by different contributors have changed the project over time. So it's like having a time machine for your project's history. So instead of the usual saving different versions of your files on your on your computer with different names, such as draft doc final, draft doc final this one, you have the same files, but you're able to access the different versions of those files, just like using Time Machine on Mac. Services such as GitHub, GitLab, and Bitbucket add a web-based social and user interface to version control. And this really facilitates open and collaborative research by enabling you and others to work together on projects from anywhere. So I've got a video here, hopefully it'll show in a second, of a very old copy of my GitHub repository and how I've used it. So for one of my papers, I've put all my files, all my software, some DAT files, and it's a really, really great way to showcase your work, to share it, by using a link. It can really serve as an online portfolio and webpage for your work. In addition, it's archiving and backing up your files and allowing others to view and contribute as well. So I'm not sure if this summer school is going to go into GitHub, but using Git is really fundamental to reproducible research, and we'll learn more about that tomorrow. So my next piece of advice on our reproducibility spectrum for sharing your code and data is to make your data open and fair. So we heard a bit this morning about how fair data is embedded into the Escape project. And And what does that mean? It means that your data is findable, accessible, interoperable, and reusable. So for example, your data should be described with rich metadata. So basically all of the information that you need in order to understand that data set should be assigned a globally unique and persistent identifier. So a digital object identifier, or a DOI, is one example of this. So for example, I've shared a DOI to my talk here, and it basically, this is unique, this is persistent, so it will last forever, and it will always point to that research output. So it's really, really important for preservation. And registered and a searchable resource. And I'll share more about that in a second. For accessibility, it's important to provide information on how to access the data. So very simply, you can share a DOI link and say, you can access the data here. Interoperability, the data usually need to be integrated with other data or interoperate with applications or workflows for analysis, storage, and processing. So we heard a bit about this morning about, especially with multi-messenger, multi-wavelength astronomy, we need data sets to be able to work together. So having, community-based and community standardized formats is important for that. And then finally, the main end goal of doing all of this is that we want our research and our data to be reusable. So it's important to share your data with a clear and accessible data usage license, and detailed provenance. So, how you went from the raw data to your final results, so that the results can be reproduced and built upon. And so a really easy way to do this is to share your data in a repository, such as Zenodo or Figshare. So these sort of catch-all repositories allow you to share research outputs in a wide variety of formats, including text, data sets, audio, video, and images across all fields of science. Zenodo was helped develop by CERN, so it's already widely used in this community. But it allows you to display your research outputs and get credited by making the research results citable, which is what we all want, and integrating them into existing reporting lines to funding agencies such as the EU. So basically, you can deposit your data set into Zenodo. You add some metadata up here, some information about your data sets. And what Zenodo does is it gives you that digital object identifier, that DOI, so that unique and persistent link that will allow others to easily find and access your data set. So it allows for easy access and reuse of shared research outputs. And finally, you can also archive your GitHub repository and make it citable with Zenodo. So I'll show some examples of that later today as well, but you can really use it to deposit anything almost. And very recently, Archive now supports sharing code and data associated with your articles. So they've got a blog post about how to use this new feature. But basically, you can link your GitHub repository or your official code associated with that paper and use, I believe it's paper to data, or there's some websites that they use to help you share your data as well. So you can add links to those. And yeah, this is really, really great. And I'm glad that they've come out with this. So those are all options and ways of sharing your data and making them open and fair. And then finally, in our reproducible spectrum, we have linked and executable code and data. So my advice here is to document methods and share analyses using something like open notebooks. So notebooks and notebook environments such as Jupyter are documents that contain equations, visualizations, narrative text, and live code that can be executed independently and interactively with the output visible immediately beneath the input. So it provides this really comprehensive story of your research methods. And you're going to hear more about this, I think it's later today by Enrique, about using notebooks. And it's a really, really great way to add context and documentation around your methods and your results, and allows people to see exactly the code that you've used, the result that you should get from running that code or software, and then you can display results. So it really brings together analysis descriptions and results, which can be executed to perform the data analysis in real time. And this adds a lot of value because it adds transparency in the analysis of the data. It allows somebody else to easily reproduce your results, and it provides documentation of your entire workflow. So it basically writes your method section in your paper itself. But it worked on my computer is something we hear a lot. So, even if you do and take all of the steps that we've outlined already, so, you've shared a link to your code, you've shared a link to your data, you've shared a link to your, or you've shared, your GitHub repository that might have your notebooks inside. But even the simplest things, such as using, a different version of Python or, a different operating system, can have consequences on the results. So that's why it's important to also capture and share your computational environment. One way to do this is through containerization, such as through Docker Singularity, which allows you to basically package up your entire research workflow, including your data, your software, your analyses, and your computational environment, so that it can run uniformly and consistently on other infrastructure. So they're a lot more lightweight than virtual machines. And the real benefits that they have are that they bundle up dependencies. So, if you're working with a collaborator, if they want to run your analyses, they don't have to, go through and install a bunch of dependencies and make sure that everything's, the same. It's all already bundled up. Containers are really easy to distribute and share, and they're stackable. So if you have an existing container and you want to add something to it, you don't have to start from scratch. You can build upon it. But if containerization maybe scares you a little bit, it might be kind of the next stage of your reproducible research journey. Another way to make it as easy as possible for others to reproduce your work is to use Binder, and they're using it in this school as well, so hopefully you have an opportunity to check it out. But Binder makes it very simple to generate reproducible computing environments from a Git repository. So basically what it does is it generates a Docker image from that repository, which should have components such as configuration or requirements or runtime files, basically defining all of the dependencies that you need, along with your Jupyter notebooks inside. And it'll spin up an environment on the cloud, and it can be easily accessed by a URL. So it'll generate a URL, you can send that URL to your collaborators, and they can immediately begin interacting with your notebook environment in the cloud. So this is a really nice kind of cartoon of how this process works. So, Jane has written a paper based on her experiments. She would like anyone to be able to reproduce, check, and improve her calculations. So she describes the experiments as a notebook, mixing prose, code, and visualization, and resources such as the source code, data, and media. She publishes them on a publicly hosted repository, such as the ones that we've mentioned so far. And then she makes that repository Binder ready by describing the software required to run the notebook. So here's, her configuration files, she's got her notebook inside and other resources. And, by linking it up to Binder, everyone can now run and reproduce her computations. So it's a really, really easy tool to use. It makes your whole research workflow just extremely accessible, and very good for busy PIs. You can just send them a link to your Binder, and they can begin interacting with your work immediately. So those are a few steps you can take to make your research more reproducible. There are many other ways and tools that you can do this, and it will also vary from domain to domain. And I think this is another reason why people might struggle to get started with open science and reproducible research is just the sheer volume of opportunities out there available. It's hard to know where to start. But I would say start small, start where you're comfortable. So the first thing you could do is, share an article on arXiv and go from there and steadily build up these reproducible and open practices in your research workflow. But there are lots of other, tools here along the whole research workflow, from, sharing grant proposals, up through sharing your analyses, up through writing, publication, outreach, and assessment. So, here's, an example pathway through that. And the one that I just walked us through is basically, discovery through open access publications, doing our analysis using a Jupyter notebook. We might write up our publication using Overleaf, which is a really handy collaborative LaTeX tool. We'll share a preprint or a postprint of our research publication on the arXiv. We'll share our data on Zenodo. We can share our software and our code on GitHub. And then, of course, we can't forget to disseminate those results. So I like to use Figshare for sharing my presentations like this. It contains them all into a nifty profile for you and generates a DOI just like Zenodo. You can tweet about it then, tweet out a link to your DOI so that others can find and access your work. And then there are different ways of assessment, but I'm not going to go into that today. Right, so we've gone through a few ways of making your research workflow more reproducible and open. I'm now going to share some examples that are done in astronomy because that's my background. So some examples for open access is, of course, the archive. So it started in August of 1991 and provides open access to almost 2 million e-prints in astro and many other and physics and many other fields. It's a hugely valuable resource that I think we all took for granted, or at least I took for granted up until very recently. So not all research communities have an open access literature archive like this. So it's a huge value to our community. In astrophysics, we also have the Astrophysics Data System, which is another literature database, which provides all of the metadata around publications. So you can, search, for publications by authors. It has a lot of, citation and index information and a lot of other metrics. So that's really great for searching as well. We share raw data via instrument archives. We can share surveys through the use of Vizier. And then metadata through Simbad. So Simbad allows you, to search for, a particular object of interest. If you have a star that you're researching or observing, you can search for it in Simbad and access a lot of its metadata and other research associated with it. And then some open source software examples. We have projects and tools such as AstroPy, the CASA pipeline for eMerlin data. Some citizen science examples include things like pulsar hunters and galaxy zoo. Open educational resource examples includes, of course, the Escape Summer School, where everything is available on GitHub for you to access whenever. AstroEDU provides a lot of resources for teaching astronomy as well. But I want to kind of emphasize examples of equity, diversity, and inclusion in astronomy as well. Even though there are examples of it, we still have a very long way to go in order to creating a more equitable and inclusive astronomy, astrophysics, particle physics, research culture in general. But we are taking steps, but we all do need to work together and be more vigilant in this regard. But some examples include the Astro Better Diversity Wiki. There's a huge list of resources there for how to, be a better ally. The European Astronomical Society annual meeting, which was formerly known as EWAS. It has sessions dedicated to equity, diversity, and inclusion. So if you attend that, I highly encourage attending those sessions. And then a UK-based project is the DARA project, Development in Africa with Radio Astronomy. So you can find out more about a lot of these initiatives. There was a Nature Astronomy focus that they published and the links there. But again, this is an area that we definitely need to work extra hard on. So next, I want to give a couple of case studies to show you that this does actually work and why it's open, why it's good to open up your research workflow and that you can actually benefit and have impact by working in this way. So in the first case study, we're going to focus on this project on constraining redshifts of unlocalized fast radio burst by Charlie Walker et al. So here's the publication. They shared their preprint on arXiv. It was deposited here, it says, on the 4th of April, 2018. So we have a nice big check mark on our publication. If you open up the paper and go into their concluding remarks, they have a link to a Zenodo DOI where you can access their Python code and examples. So if you click on that, it brings you to the Zenodo archive of their GitHub repository. So this is what I was saying earlier about how you can deposit and save a version of your GitHub repository in Zenodo and make it citable. So if you look in their repository, you can see things that they have, Python scripts, an IPython notebook. They've got some text files, and they've got their data files in their Zenodo upload. So here we go. We have our code and we have our data. So if we click through to their GitHub repository, there's a link there from Zenodo. This is probably a lot more friendly to look at and read than the Zenodo archive version. But here you have their README, and if you look a little bit closer, we see that we have a link to launch Binder, so that that really easy way to access their Jupyter notebooks. So if we click that, it'll spin up a Binder environment containing everything that was in that GitHub repository. So they had included, their data sets, their scripts. They have, requirements.txt, runtime.txt, everything needed in order to spin up this computational environment in the cloud. And then what you can see is you can easily access their notebooks. You can see their analysis. You can rerun and interact with their analysis. So yeah, linked and executable code and data, check. So they've done all these steps. What is the impact of that, and why should we do this? So they submitted the manuscript to the journal and deposited a preprint to the archive on the 4th of April, 2018. And within 5 days, they received a referee report, because the referee was able to very easily reproduce and view their results and understand how they came to their conclusions. So that's really great, because it can take months for the review process. So yeah, make it as easy as possible for other people to produce your work. The official publication didn't happen until June 2020. And this can happen, maybe you're in the middle of your PhD, or you're at the end of your PhD, or you're moving jobs. It can take months to years to actually officially publish a paper in a journal. So that's another reason why it's so important to share your work open access via something like arXiv, so that you can get it out there as quickly as possible. And so because of this, because they had shared their article on arXiv, they had received 14 citations before it was finally officially published by the journal. And it's got 21 citations to date. So it just demonstrates how important it is to share your work, and how you can succeed and have those measurements of success that we need to kind of progress. So the next example is one that is probably familiar to most people. It's the very exciting results of the first image of a black hole. And this is a really good example of open science and openness and reproducibility within a big collaboration. So this is ultimately what we're working towards with open and reproducible research. So when this came out, they shared it via the Astrophysical Journal letters, but they did share everything open access. So it was published in an open access journal, and you could immediately access everything without logging in, without paying to access these results. And this allowed everybody across the world to access as well, which is very, very important. They've shared links in their paper and on their website to their various data products and source code. So if you look here, they've got their data products and codes for all of their projects. This particular paper was the one from 2019, so we'll focus on those. Here they've got a link to their GitHub repository, so we'll go there, and you can immediately access the software that they wrote in order to perform their analysis, and check that out. They also have a link here to their calibrated data products. So if you click, checklist for publication and code. Next, they've got their data available linked there via a DOI, a digital object identifier, that takes you to the data commons, where you can access their calibrated data. So check, we have coded data. And then finally, if you go to their GitHub repository, their kind of organizational one, if you looked in their pin repositories, they have Docker recipes. So they have provided the recipes that you need in order to have the same computational environment that they use to run their software and conduct their analysis on their data. So check on linked and executable code and data. And, we all felt the impact of this. This was a very exciting result, and it would have been impactful either way. But the fact that they, were transparent and reproducible the whole way through, I think just makes it all the better. But they, submitted their manuscript. These are the statistics for paper one. They had quite a few papers come out at the same time. For paper one, submitted March 1st, 2019. A couple weeks later, accepted by the journal, officially published a couple weeks after that, and has received over 1,000 citations to date. And so, you can see how many downloads it's had, from the Astrophysical Journal's website. You can access all of the, citations and the work that's been, that has built upon it, on ADS. And then in June of 2019, so a few months later, they deposited a postprint to the archive. And yeah, the impact was just phenomenal. And it was a really amazing example of collaborative, open, transparent, and reproducible research in action. So that's a lot of information, and there's still a lot more I could cover, but we'll leave it there. So I want to leave you with some takeaways and some further resources. So the Turing Way is a really handy resource on reproducible research. It's a project that's led by Kirsty Whitaker at the Alan Turing Institute in the UK. And its goal was to make reproducible research and data science too easy not to do. So the project encompasses a handbook. So the handbook includes kind of chapters on reproducibility, open research, project design, collaboration, ethics, and community and outreach. They have a community, so a really interactive and engaged community on Slack and Twitter. It's a collaboration. They have workshops and training. So they want to also upskill people in reproducible research. So I highly recommend getting involved in this project. It's a team of researchers, research software engineers, librarians, and you. Like, everybody is welcome to join and, learn from this project, to contribute to this project. If you see, that something's missing from it, you're very welcome to contribute. They have onboarding sessions every week. And if you have a really good case study of your work that you think would demonstrate some of these practices, then you can also feed that back into the book. But importantly, the project itself also demonstrates open and transparent project management and communication with future users, as the whole thing is openly developed on GitHub. So you can see exactly how everything is done in working on the book, but it's also a really valuable resource. There'll be a few talks later this week by Arturo on reproducible science in practice. So I think he's going to go into a bit more detail on how ESCAPE does this, and you can learn a lot more information there. I've got a few resources I've developed myself. So I've got an introduction on using GitHub if you want kind of a more in-depth look on how to use that platform. I've got a short course on reproducible research through containerization using Docker and Singularity. So really simple examples on how to containerize your workflow and why it's important. And then if you feel like after this course, you still need maybe further instructions or further material to learn, software and data skills, the Carpentries have a lot of great workshops that you can either take in person, or all of their materials are open source online if you want to take a look, to really help you kind of hone these computational skills for data science. And so finally, I'll just leave you with a few takeaways. From that initial paper I shared at the beginning. Reproducibility is like brushing your teeth. It is good for you, but it takes time and effort. Once you learn it, it becomes habit. So I've shared a lot of platforms, a lot of different pathways to open and reproducible research. And that's not to overwhelm you, it's not to scare you, but it's to show you that you have a lot of opportunities to get involved. And as scientists, as researchers, we get really excited about learning new things. We're quite curious. So have fun with it. There's no reason to get overwhelmed. I always tell people, if I can do these things, I feel like anybody can do these things. But yeah, so I would just suggest, start small, test out one platform or open up one stage of your research workflow, such as sharing your data to Zenodo and linking to the DOI in your publications, just baby steps to start with, and it'll become habit and easier to do and easier to add more as you go. And all of this is just to say, please help us build a kinder and more inclusive research culture. So yeah, thank you so much for having me.
Thank you so much, Rachel. Really, really thank you so much. In fact, for being there, and also because you already made my job much easier. So thank you. We have some time for questions, so I will essentially read some of these to you. But just to let you know, there is already some debate while you were talking. So I will try to summarize also that part in the channel that was assigned to your talk. So I think the first question here is, do you think that the reviewing code should be part of the peer review process to publish a paper? And if so, should and how can this be enforced?
Yeah, so my short answer is yes, I do think reviewing code should be part of the peer review process to publish a paper. I think a lot of the challenge here comes from finding enough reviewers to do this. And I think there's already some challenge to getting reviewers for papers kind of without reviewing other aspects as well. So this is something that does need to be incentivized and rewarded a bit more. People will need to be credited for this in order for it to probably really take off. So I already see that there's a really great example that somebody shared in the Slack on the Journal of Open Source Software. And it's a really cool platform for publishing your software and your source code. It's all done via GitHub, and that's a really great process to do it. But there are also code review clubs kind of popping up around various institutions. So I know Oxford's got one set up where it's more of a peer-to-peer kind of experience as opposed to a formal one through a journal. But that's kind of a great way to start the process of peer reviewing code. Back to the actual question, do I think reviewing code should be part of the peer review process to publish a paper? Yes, I think as like what we said at the beginning, as a minimum, a reviewer should be able to reproduce the results using the same data and the same code. How can it be enforced? Yeah, you just need to incentivize it and reward it and give people credit to do it. Yeah, I hope that answers that.
Thanks. Yes, and I think it matched what you said. If you make it like the example that you put on make it easier for the reviewer to review the code, that will also will happen easier. So the next thing about next question, let's say, is I guess it's a kind of mixing an opinion here that those that don't work in academia, but I guess the question is still do research, still developing something that can be useful. Should they disclose this research and the code? But again, it's always the discussion about the private and public property of this thing.
Yeah, I do think that's really tough. Most of my advocacy comes from, I believe that publicly funded research should be made publicly available and accessible. It is probably harder to make that argument for private research. That's probably beyond my expertise. If I had an opinion, I think that if a more independent and private research project, gets, wants to go through that process, if it's a similar process where they want to have, these real world outcomes and benefits to society, then, at least at the very end, share as much as they can. There's another quote called "Open as possible, closed as necessary." So depending on the domain, if it's something where you have like patient data or where you have sensitive data, you really cannot actually just share that. That does need to be anonymized and stored in very particular and safe ways. So that is where I would probably diverge a bit. But yeah, that's a really good question, and I'm not actually sure I have an answer to it.
No, thanks. No, no. Again, it's very complicated to encapsulate all these different scenarios.
Yeah, I think philosophically, I think they should, but yeah.
They have another question. I guess it's very popular. Also, is when you were mentioned about this gold standard when you are able to share data, code, and everything, and somebody can really reproduce what you are doing. And this fear, can be playing against you. If it's somebody with more human power or computational power can take it from there and go obviously faster than you, just because and if that is help can be a way to see it as it's playing against you.
Yeah, and that's sort of like I mentioned at the beginning, that there's a lot of fear around opening up, and that is the biggest barrier. And it is a possibility right now. The incentive and reward structure is to publish as much as you can, as fast as you can, and it matters kind of where you publish as well. And so that's why there's also this simultaneous push to really improve research culture. And so like, it's almost circular. Like, I believe that, working in a reproducible way and practicing open science will improve research culture. But at the same time, research culture has to keep up in order to nurture and facilitate this way of working. So one way that I do think that sharing your, publications in an open access repository, sharing your data, and getting a digital object identifier for it, and sharing your code on GitHub, is all of those things are time stamped. So you have a record of when you've done something. So if somebody in the community does like come in and they're like, oh, I can do that faster because I have more resources, you can prove that you were already working on this. And I don't know, for me to see somebody try and scoop somebody else when everything is that visible, I hope that other person wouldn't kind of progress in that way. I hope the community would kind of come together and recognize what's happening and work to eliminate that kind of behavior. But what I would like to see is, instead of a different team coming in and trying to steal that data, is being like, hey, we have the resources, we have a larger computer to work on this. Would you like to collaborate and we can work on this together? And that's really what open science and reproducible research is all about, is really cultivating a stronger collaborative, culture like that. So that's what I would like to see.
Thanks. In fact, Dimash also, but the people again is discussing what we are talking here. So, so the next question is when sharing the data sets, and also again depends a lot about the experiment, but should I share the raw data or the reduced data? I mean, the data set is passing, the data set that is passing after a pipeline to produce and reduce the data. And again, the different opinions about that depends.
Yeah. So I guess it depends on your domain. I think there should definitely be different versions, from the raw data to the final analyzed data set. In astronomy, this is quite easy because the instrument archives usually share the raw data themselves. So usually after an embargo period of usually a year, you can access the raw data from telescope archives. So you could link to that instead of downloading it and hosting yourself. You could link to where that exists. But yeah, I would say when you're structuring your your repository or your directory where you're doing your analysis, having a read-only version of the raw data is really important, and then having a separate directory for processed and analyzed data. So that's where provenance comes in, really documenting and demonstrating how you went from the raw data to the kind of final data sets. Does that help?
Thanks. I think, again, let me just throw my own question here. Do you think that also means the usefulness of that raw data? Sometimes it's so big, it's so, like the discussion is happening here, they say, okay, it's open, but it's not something that somebody it's not an entire country can buy the computers to analyze it. So
Yeah, and that's another huge issue. I did mention that very briefly at the beginning. Just because something is open doesn't mean it's accessible, and this is increasingly going to be a challenge. And that's where projects like Escape really help, because they provide and things like the SKA regional centers, they provide the infrastructure to house the data and process the data, so that people can just log in and ship off their container and run their analysis pipeline without having to download anything to their individual machine or their local cluster. It's all handled by that big project infrastructure, and that's why these kind of projects are really important, because just because it's open doesn't mean that anybody can download it and reuse it. That's a very good point. Yeah.
Thank you, Rachel. Again, one question related with what you mentioned before about the reviewing of the code. Did you have any idea how this can be promoted? Or I know it's a hard question because people is already also discussing, but do you find ways where maybe it's already happening or it's already at least proposed to get how the people can get credit for that, to do something that is not in the background job?
Yeah, it is. It's a good point. How can we do this? So at the Software Sustainability Institute, we're advocating for this a lot. So we are working a lot with policymakers and funders, who I think is probably who we really need to advocate this to. And how can we promote reviewing code to our agencies so we get credit for that? Yeah, I think if you can find a way to demonstrate the importance and show that to your senior team members locally, and then they can advocate for you to more senior leadership in the institution and kind of work your way up that way. Talk to your local research software engineering team or department. If you have them, they would have great advice probably on that. But promoting and reviewing code to our agencies. We're doing that as an institute at the Software Sustainability Institute, really liaising with funders and policymakers. If your kind of local societies or funding agencies have events or town hall meetings, maybe you could attend those and raise it on the agenda there. That's where I would start.
Thanks. And I guess also this kind of collaborative tools that you show also is record anyway. You were talking about timestamp, so it's record who also did that. So you can use this in your favor, no?
Exactly. And as far as getting credit for that, I would start advocating for that yourself. So if you and your team and your project go through the code review process, make sure you acknowledge that in your papers. A lot of journals have acknowledgement sections where you can thank people formally for how they've contributed to your work. So I think that's one way to provide credit. But in terms of kind of getting the credit that you need for career progression, these are all still things that need to be implemented by our institutes and by funding agencies, is to provide those rewards for these things. So I would definitely add them to your resumes. I was involved in code reviewing, and the more that we normalize this, the more we can start to see the change. The Royal Society that I mentioned earlier in the UK about their research culture kind of policy project, they have a template for kind of a researcher resume. So it's a more narrative CV where they ask you, to go through some questions, like how have you contributed to your field? What impact have you had? What data have you shared and worked on? And how have you mentored others? And these kinds of questions around collaboration and collegiality. So we are piloting some of these things in the UK. It's now getting kind of your institutions and your universities to incorporate that into their, promotion and hiring practices.
Thanks again, Rachel. I will take another one here that I guess it matches with what you were saying about collaboration, because this is one of the problems of the issues to replicate a result or the analysis is that you don't have enough access to power for computer as the original research, and so the question is how to overcome this. But I guess that that goes, sorry, with the collaboration that we mentioned before.
Yeah, I think collaboration can be really powerful for this, because this is an issue in order, as research advances and technology advances, what we do becomes more resource intensive, and not all institutions can afford those resources. Not all researchers can. So collaboration is key, and projects like Escape and places that can provide access to those resources is really important. I don't know if that answers the question.
Thanks. Yeah, and I guess that when you mention also, when you put something, it's an original idea, it's already a timestamp, it's already an author, that somebody can help you because you lack that power, but you have that creativity and put the two things together too. There is more specific question, but I see that we still have a time. I don't know if we go for this one, like very specific, like when you should use Zenodo, for example, and MyBinder. How hard is to update the code when it's already there in those platforms?
Yeah, that's a great question. So you can do this whenever you want, because it's all versioned. So if you're working in your GitHub repository and you kind of want to get that DOI in place, that identifier in place, and that timestamp in place, you can archive it in Zenodo at any point. You can update that with different version releases through GitHub. So there's, I can share a link in the Slack after we finish answering questions, but there's a whole kind of pipeline where you can automatically have your Zenodo version updated every time you do a GitHub release. So every time you do an official GitHub release, it automatically pushes the latest version to Zenodo. And with Zenodo, you'll still have that kind of base persistent identifier, that DOI, that you can share, and it will always point to the latest version of whatever you've uploaded to Zenodo. But if you have multiple versions of either data or code on GitHub, you can also access specific links to each of those versions if you want to be like, this, output a different result than this version kind of thing. And that's what's so powerful about digital object identifiers and versioning and version control, is that you can directly compare everything. And so the process is actually quite simple. There's a lot of documentation on Zenodo and on GitHub for doing this. So it's not hard to update at all.
I mute myself to don't interrupt with my breathing here. Yes, so thanks again. I think the part of the MyBinder also mentioned, I guess it's the same that you were saying, that it will update anyway, so it will. Yeah,
so with Binder, you basically paste a link to your GitHub repository in the Binder kind of homepage, and then it spins up based on that. So if you have a specific version, you can either, I don't know if you paste the link to the specific commit, but yeah, there's a way to update that. Yeah, it all should be documented on those websites, but it's not too much overhead at all.
Thanks. Yes, exactly. You can put the tag, so you will be permanent to that particular version. But if you put the master, you will learn more about that. If you still don't know, you will get the latest version every time.
Yeah. Exactly.
So here there is another, also but very, very specific, there is some limits in the amount of data that you can put in this kind of platform. Sorry, I have one, and I think I skipped it, but now, sorry. Oh my God, just 1 second, because it was a question about, yes. can this very large amount of tools be prejudicial to the open science standard? I mean, when you choose one path, and I guess that was the slide when you were like try to navigate to different logos and platforms. You choose a path, but there are thousands of different paths that to choose and can get messy.
Yeah. Sorry, I'm not sure I see where the question is, but so yeah, something I do want to stress is, choose the platforms and the process that works best for your individual research case. For example, the workflow that I went through kind of in depth, from archive to GitHub and Zenodo and things like that, those are quite general and should be mostly applicable to everybody within the physical sciences. But, different domains might use different platforms or have a different workflow and different tools. So a good example of this is in psychology. There's this huge movement to pre-register your methods. So part of their pipeline that they're working on now, or part of their of their research workflow, is that what they do is they write up and pre-register the methods that they're going to do. So, the surveys that they're going to take, the questions that they're going to ask, how they're going to analyze that data, kind of thing. They're going to say all of this up front and submit that to the journal. And then if the journal, accepts that or approves that, then basically they're being published regardless of what the end result is. It's the research question and the research methods that's being evaluated. And so then after that, it doesn't matter if they have a null result or an insignificant result or no result, or if, even if they do have a positive result, it'll get published alongside their pre-registered report anyways. And so that's something I didn't touch upon because it hasn't really made its way to the physics community yet, from what I can tell. But I don't know if I've gone completely off tangent of what the question was, but basically you don't have to use all of the platforms. You don't even have to use the ones necessarily that I suggested. I would definitely use the ones that work for your particular science use case and, project and question like that. So was that question in Slack? Did I answer it?
Yes, no, yes, it was there. Sorry, it was my fault because I overseeing that. But yeah, it was like this worry about, there are so many options that maybe can be not the best idea, but
yeah, and that's why I think it's a barrier to get started, is because you look and just getting started with something like Git or GitHub itself can be quite overwhelming. So when I first started, I'm by no means a software developer, but we all need to have some experience of programming and software in order to do our research. That's just the nature of our research these days. And so, when I first started with GitHub, if you saw my kind of short video at the beginning, it was my kind of productivity chart on GitHub. It was totally empty because it was just, I did find it overwhelming. But then once I finally, learned the skills and, how to use the version control aspect, in Git and how to use it, it completely transformed my workflow. And it's really great for collaborating. It's a really great backup. If you can't find, a script that you wrote, last year on your local machine, if you upload it to GitHub, you're never going to lose it. It's always going to be there. And you can see how it changes over the course of your project through version control. And it's also really great for project management and collaboration because like with things like GitHub and GitLab, like you can create issues, which are, effectively like to-do lists. I need to do this to my script or to my, project, and it's easy for other people to comment on. I should also say that if you're not ready to open source and share your code publicly yet, GitHub also offers private repositories. So you can practice and, get confident and comfortable using it and developing those skills. And then when you're ready, that's when you can make it public. So, don't be don't be scared. It is overwhelming, and that's why I try and pause when I go through all the platforms, because not all of them will apply to everybody. And just take it slow. Start small, and build up as you go. And attend things like this where you can learn the skills.
We still have a few minutes. I see also a comment here from Maximilian, in the sense that maybe I can put some of these things together, because I wanted to ask you myself. Sorry, I have the opportunity, but more of the discussion also is happening like a lack of resources, or not lack of resources, but difference, very heterogeneous environment. And many times it's the private companies that fill that gap. Watson mentioned that some private company even give you for free until a certain amount. You mentioned GitHub, that we mentioned many times here, is also a private company that is in principle giving this away in some sense. How you see more and more on these kind of, I would say, collaboration also between the two?
Yeah, so I think this is a really important thing to bring up, is the importance of open source software and development and collaboration. So the reason I kind of promote GitHub in this talk is because that's what most people use. But as has been said in the Slack chat as well, like, it might not always be around, and it is a private company, and it could go any day. And that's where the real importance of the open source software community comes in. So platforms like GitLab, which is effectively the same thing, but it's all open source, is really what we should be using. But currently there's not a whole lot of funding for maintenance and upkeep of these kinds of things. So there are really successful projects, such as Astronomy and things like that, who are really doing well. But it's not really consistently there in our research culture yet to fund kind of consistent, maintenance and upkeep and skills related to open source software. So this is something else that we're also pushing from the Software Sustainability Institute, is to kind of put pressure on funders to include this as well, because it's a really good point. And that's why Zenodo is really good, because it's got that backing from CERN, and I think it's meant to last for a long time. Whereas if you use a more private data repository, it might not always be there. So yeah, that's a really good question. I don't think I can.
No, I was maybe thinking in the opposite, in a positive way, that the fact that this is happening. So as researchers, if we're using open source software and platforms and tools, it's really important to give back to those platforms and tools. So if you're using it, if you come across a bug, maybe instead of ignoring it, open up an issue, or if you have the expertise, offer to help fix it, kind of thing. So it's really, open source is all about community, and I think there's a lot to be gained there. I think the only thing really lacking is probably the funding at this point. So maybe the last, thank you, Rachel, again. I am trying to connect what Maximilian writes, and that about the major component of this reproducible science is the workflow automation and the tools and the building. So I get that he mentioned about tools like Make, SnakeMake. I guess that connect also what we were talking about, the containers and the containerization of these environments. And how much, I guess the question is how much relevant is, and we should pay more attention to this. So to make it, almost a one-click reproducibility.
Yeah, definitely. And I didn't spend a whole lot of time on automation, but honestly, automate as much as you can. And I left most of that out because I knew it'd be covered, or I think it's going to be covered later in the school. But the more that you can script and automate your process, the easier it is to go and reanalyze something or change or change your method, or update or adapt your method kind of as you go. So that example at the beginning, where if you submit a paper for publication, maybe it takes a few months to get the referee report, or maybe it takes a while to get, some feedback from a collaborator. And they're like, oh yeah, but what if you tweak this, or, what if you did this instead of that? And to try and, weed through your local, directory on your machine and try and find out, exactly what you did can be a real struggle for some people if it's not already scripted and automated. So I highly recommend scripting as much as you can so that you can easily go in and adapt it and then rerun it. So I think there are going to be talks about, continuous development and integration and testing and stuff in the school. I wish I had those skills when I started my PhD, is all I can say.
No, thanks. And I think we may feel the same way. This is why we try to create this. So we have 5 minutes, a little bit less. I don't know if I don't have more questions in the chat. Unless I miss another one, but I don't think so. I don't know if you still wanted to share something else with us. It seems
yeah, so well, I just want to say I've been kind of following this school. I haven't ever attended before, but I've been kind of following the GitHub repos of this school for a few years because I think they're just really phenomenal resources. And I've referenced, I think, the Git slides a few times in the past before as well. So yeah, really excited about the school and what the participants are going to learn. And I'm really glad that, even though we can't be together in person, that it's really accessible for a whole lot of people this time. I think there's 1,000 attendees, which is really, really great. And I hope you all get a lot out of this. But yeah, I would say, yeah, if you do kind of get overwhelmed, if there's a lot, there are a lot of resources these days online. So I'll just reemphasize the Turing Way. It's got, most of my content, information and how-tos come from there. So you can always access that for further information. But yeah, just help us make research culture better. That's my final thought.
Thank you. No, thank you so much, Rachel. Again, thank you very much. And you can also see in the chat, many people is saying the same. Great talk. Thank you so much. Great lecture. So thanks again for you for all the presentation. I just reminded the people, some others were asking about the links. I send the link to your class, to your lecture. And yes, thank you very much. And again, thank you also for the people for much of people, the questions that you made.
Thank you so much for having me.
So yes, this is, sorry, I was dealing with the question and also with the agenda here, but so this is in principle ends our morning sessions. So thank you very much to everybody for being here. We will have an hour and a half break for lunch for those that are lunchtime, but in general, I say a break, and we come back at 2 p.m. Our time for the next classes and the next lecture. Thank you very much for being here.